So if you've ever stood beneath a totally massive skyscraper or, driven across a sprawling bridge, you might have actually wondered, how in the world do these colossal structures not just sink straight into the earth? Well, the answer lies in a really fascinating, hidden world of deep foundations operating right beneath our feet. Today, we're going to shed some light on that underground engineering marvel in this explainer on the incredible science of pile foundations.
Okay, here's our roadmap for today's explainer. We'll start with the deep foundation solution, then look at classification by function, materials and installation, load capacity and transfer, the power of pile groups, and finally, selecting the right pile.
All right, let's jump right into Section 1, the deep foundation solution.
This really brings us to the ultimate engineering challenge that builders have faced for, centuries. How does humanity build massive structures on weak, soft soil without them just completely sinking? I mean, when an engineer arrives at a site and the surface soil is incredibly soft or loose, a standard shallow foundation just isn't going to cut it. If you try to place heavy loads, think bridges or multi-story buildings, on that kind of ground, excessive settlement or even total collapse is practically guaranteed. So what's the fix? You have to go deep. Enter the hero of our explainer, the pile foundation. Think of piles as incredibly strong, long, slender members, basically underground stilts. Their main job is to just bypass those problematic, weak soil layers near the surface and reach all the way down to transmit those heavy structural loads directly into the much firmer, harder strata located deep below the ground. You can really see how a pile acts almost exactly like a structural column. It literally drives right through that upper weak soil layer, completely ignoring it, just to find a solid, immovable footing on the hard stratum way down below. It's a super elegant, simple concept, but the engineering behind it, absolutely precise.
Now, what I absolutely love about this is that it's not some brand new idea. The history here is staggering. We're talking 12,000 years ago. Neolithic inhabitants in Switzerland were driving wooden poles into the soft bottoms of shallow lakes just to elevate their homes above the water and away from predators. Fast forward a bit to 59 AD, and the legendary Roman architect Vitruvius officially recorded the use of pile foundations, and today, they remain the single most common type of deep foundation used globally whenever soil conditions are just not cooperating.
Moving on to Section 2, classification by function. So now that we know what they are, we can actually classify piles by how they transfer their load into the earth. And there are two main methods here. The first is end-bearing piles. Just like that concept we talked about a second ago, these transfer their load directly through the very tip of the pile to a hard, suitable bearing stratum underneath the soft soil. The second method involves friction piles. These are used in really deep, homogeneous soils where there just isn't a hard, rocky bottom nearby. Instead, they transfer loads into the surrounding material via skin friction along the entire surface area of the pile shaft, kind of like holding onto a pole. In reality, though, almost all piles develop a combination of both end-bearing and skin friction, but they're classified by whichever method is doing the actual heavy lifting. But wait, it doesn't stop at bearing downward weight. Piles are incredibly versatile. You've got tension piles, which actually resist upward forces, like keeping a buried tank from literally popping out of the ground because of groundwater pressure. Then there are compaction piles, which don't even carry a load. They're just driven in to compress and strengthen loose granular soils. We've also got anchor piles against horizontal pull, fender piles acting as massive bumpers to protect waterfront docks from docking ships, and sheet piles that interlock to hold back water seepage. Oh, and if you need to resist horizontal forces, engineers use batter piles, which are actually driven in at an angle.
Okay, Section 3, materials and installation.
So the choice of materials strictly dictates the maximum design load. Take steel, for instance. Using rolled H-shapes or really thick pipes, it can handle massive loads of over 1,000 kilonewtons. That is upwards of 100 metric tons. Timber is fascinating too, because it performs beautifully if it's either entirely dry or entirely submerged in water. But if the water table fluctuates and that wood alternates between wet and dry, it rots. That's exactly where composite piles come in. You can use untreated timber for the permanently submerged lower half, and then top it with concrete for the part that projects above the water table. Pretty clever, right?
So once you've picked your material, how does it actually get into the earth? Well, the first method is straightforward but requires some massive dynamic energy. Driven piles. Using heavy drop hammers, steam hammers, or vibratory equipment, these are literally pounded into the ground. The second method is cast in situ. This completely eliminates the intense vibration of driving. Instead, holes are carefully drilled into the earth and then filled with fresh concrete right there on site. And finally, there's a combination method, like the famous Franke pile, which uses a driven outer shell or casing that is then filled with concrete.
Let's roll right into Section 4, load capacity and transfer.
With our piles finally in the ground, we now need to figure out how much weight they can actually hold safely. The totally crucial point here is establishing what we call the ultimate bearing capacity. Simply put, this is the absolute maximum load the pile can handle before the soil fails or settles excessively. But of course, engineers aren't going to load a pile right to its breaking point. They take that ultimate capacity and divide it by a strict factor of safety to find the allowable load. This guarantees an adequate safety margin against catastrophic settlement.
Now, figuring out that capacity is a pretty rigorous process. Engineers use static analysis, applying these complex theories from experts like Meyerhoff and Vesic. They also use dynamic analysis, plugging data into formulas like the engineering news formula. But one of the most fascinating techniques? That has to be the wave equation method. When a massive pile hammer strikes the top of the pile, it actually sends a stress wave down the entire length of the column. Engineers apply wave transmission theory to this exact impact energy to calculate the pile's load-bearing strength. It's wild stuff. But, despite all this advanced math, the single best, absolutely foolproof approach is simply conducting physical load tests right there on the construction site.
All right, Section 5, the power of pile groups.
So rarely does a single pile support a structure all by itself. Normally, individual piles are strategically arranged together in a grid under the footprint of a building. They're then tied together at the surface by a really thick concrete slab, which is called a pile cap. This makes sure that the heavy loads coming down from the columns and walls are distributed super evenly across the entire group of piles.
But here's a really surprising dynamic about pile groups. You might naturally think that if one pile holds 100 tons, a group of 10 piles holds 1,000 tons, right? Well, that is actually rarely the case. We have to calculate something called group efficiency, because driving piles actually disturbs the surrounding soil, and because the stress zones of closely spaced piles overlap deep underground. The total capacity of the group is usually less than the sum of its parts. In fact, in soft clay, an entire group of piles can actually fail together as one giant block. So engineers have to carefully calculate pile spacing to mitigate all this overlapping stress.
Which brings us to our final part, Section 6, selecting the right pile.
Synthesizing all this theory into the ultimate engineering decision, actually selecting the right pile, requires evaluating some incredibly strict criteria. Engineers have to look at the exact structural loads, the deep soil profile, groundwater conditions, and even just the local availability of heavy equipment and time. For bridges, they also have to consider the flow of water and potential scouring of the riverbed. But here's a really fascinating caveat for you. Piles are not always the answer. Sometimes, a naturally firm soil layer sits right on top of a soft, deep layer. Driving piles into that firm top layer can actually punch through and break it up, destroying its natural ability to act as a supportive mat. This concentrates the stress right into the soft clay below, causing the exact sinking you were trying to prevent. Engineering is really all about knowing exactly when and how to apply the right tool.
So next time you're walking through a dense city looking up at a massive skyscraper or driving across a towering bridge, take just a second to look down. Ask yourself about the vast, hidden infrastructure of driven steel, poured concrete, and ancient engineering principles holding it all up from below. It's truly amazing when you think about it. Thank you so much for exploring this with me today, and keep asking those big questions.